NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will prove a classic inequality for the floor function and present the solution exactly in structured steps. First, we display the label and the problem statement as an example. We start with the definition of the floor function and set up x using its integer and fractional parts. Step 1. Define x by its integer and fractional parts and record the bounds of the fraction. Next, we use the linearity of the floor with respect to an integer shift. Step 2. Linearity of the floor with respect to an integer shift. Step 2. Expand the expression for k times x and use that k times n as an integer so it can be pulled outside the floor operator. Finally, we bound the floor of k times p between 0 and k minus 1. Step 3. Establish the final inequality bounds and conclude the desired result. We will prove a classic theorem about fractional parts. We follow the exact steps and rules as presented. Theorem, proof, rule boxes, and a worked example. Proof outline and rule, reminder. We will use the definition of the fractional part. Brace x equals x minus floor of x. Here is the required example and problem statement, shown exactly as specified. Step 1. Express the left side using the fractional part definition. Quick challenge. What does floor of x represent? It is the greatest integer less than or equal to x. Step 2. Decompose each number into its integer and fractional parts and substitute. Step 3. Use the floor property, floor of n plus a equals n plus floor of a for n an integer. Cancel the common integer parts and simplify. Step 4. Use the range of fractional parts. 0 is less or equal to the fractional part, and it is strictly less than 1. Then analyze the sum and its floor and conclude the inequality. Final statement in green, enclosed between the confetti tags. As required, in this example, we will prove that for every real number x, the absolute value of x minus the floor of x plus 1/2 is less than or equal to 1/2. Step 1. We decompose x into its integer part and its fractional part. Say x equals floor of x plus fractional part of x, where the fractional part lies between 0 and 1. Define a to be the absolute value of x minus the floor of x plus 1/2. Substitute the decomposition for x, and use the fact that floor of x is an integer to pull it out of the floor operator. This simplifies a to the absolute value of fractional part of x minus the floor of fractional part of x plus 1/2. To build intuition, let us visualize the fractional part on a number line from 0 to 1. We will place a point at the fractional part of x and examine 3 cases. Case 1. The fractional part is at least 0 and less than 1/2. Then the fractional part plus 1/2 lies between 1/2 and 1, so its floor is 0. Therefore, a equals the absolute value of the fractional part, which is less than 1/2 in this case. Case 2. The fractional part equals 1/2. Then the fractional part plus 1/2 equals 1, whose floor is 1. Therefore, a equals the absolute value of 1/2 minus 1, which is exactly 1/2. Case 3. The fractional part is greater than 1/2 and less than 1. Then the fractional part plus 1/2 lies strictly between 1 and 1.5, so its floor is 1. Therefore, a equals the absolute value of the fractional part minus 1, which is less than 1/2 in this case. A helpful interpretation is that the floor of x plus 1/2 equals the nearest integer to x. So the quantity we are measuring is the distance from x to the nearest integer, which cannot exceed 1/2. Combining all 3 cases, we conclude that for every real x, the absolute value of x minus the floor of x plus 1/2 is less than or equal to 1/2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.